Now let's talk about solutions, and the good news is we don't have to play this game at full price. Model compression is the answer. Specifically, compression techniques work by targeting one or all of three potential bottlenecks for inference: the compute bandwidth requirements, the memory bandwidth requirements, and the total memory footprint. The best techniques accomplish this without compromising the model's accuracy. And let's run through a quick breakdown. First, quantization leverages the fact that LLM training is extremely noisy, resulting in redundancies throughout the entire network at the baseline precision. We can exploit this by reducing the number of bits required to represent various components of the model, and therefore the memory and compute bandwidth to run through. This includes activations, waits, the KV cache, and even the attention operations. In general, this alone enables 2 to 4x faster or cheaper deployments. And extending this to training, we can use QLoRa and other techniques, making fine-tuning both cheaper and faster. Second, pruning, where we remove connections from the network entirely. This relies on redundancies built into the training process in a large search space where we converge on a much smaller optimization space after exploring through training the portion that actually matters. We can exploit this by reducing the number of parameters we need to store and skipping compute for those removed connections. With these techniques, a 50% sparse model is 1.5 to 2 times faster or cheaper for inference. Next, let's talk through knowledge and data distillation, which allows us to shrink the problem even further. In knowledge distillation, we're training a much smaller model to match the behavior of the larger one, learning from the full distribution of the outputs rather than just a single next token for the correct answer. In data distillation, we generate high-quality, enriched synthetic datasets from that larger model that enable smaller models to learn faster and more effectively. Both methods unlock the ability to deploy models that are up to 10 times smaller for specific tasks, while still maintaining accuracy. Fine-tuning and iteration times also drop significantly, allowing teams to move faster while spending less. Finally, speculative decoding takes a different approach entirely, where rather than reducing the model, we're actually extending it to improve performance. Specifically, it adds a smaller, faster speculator model that predicts multiple tokens ahead in the sequence. The larger, more accurate model then steps in only to verify those predictions. As long as we're running less compute-intensive scenarios, then verifying adds very little overhead, and we shift the memory bandwidth limited portions to a smaller model. With these techniques, we can cut inference latency anywhere from 2 to 4x. Finally, combining the techniques enables compounding gains, where a 10x smaller distilled model can be quantized, enabling a further 3x performant gains on top of that. And yet today, over half of VLM deployments are still running uncompressed models, and that's a lot of wasted compute and money. So let's dive into some examples to approximate just how much these deployments might cost.